If you were to throw a ball horizontally off the edge of a cliff and then at the same time drop an identical ball, which would land first? So this is one of the questions we're going to answer with the topic of projectiles and motion in this A-level physics video. So today what we're going to look at, first of all, is motion graphs, so distance time graphs and velocity time graphs. And then we're going to also look at SUVAT equations, where they come from, how to use them, and projectile motion. So like the example here, and the ball that's getting projected off the end of a cliff. So let's start off with those graphs then. So we've got a displacement time graph here. It could be a distance time graph for this purpose as well. If I wanted to work out the velocity from a curved line, the object is accelerating. That's what the curved line represents here, because its gradient is changing. If at any point I wanted to work out its instantaneous velocity, I would need to draw a tangent, because I cannot take the gradient without drawing a tangent. And its instantaneous velocity would then equal the gradient of that tangent, being change in distance over change in time. If I want to work out the average, I could then take the average distance and time and divide them, but there's a big difference in instantaneous and average velocity. For a velocity time graph, for a straight line, we should know that equals the gradient for that equals acceleration, which is change in velocity divided by change in time. Now, for certain objects that might reach terminal velocity, like a skydiver or like our ball here, or anything that experiences air resistance or drag or frictional forces, what's going to happen is the velocity is eventually going to become constant when, in this example, the weight becomes equal to the drag, or the thrust becomes equal to drag force, which increases over time. For a velocity time graph, the area under the graph is equal to the displacement. Now that's easy if it's a triangle or a rectangle. If it's a curve, at A-level you need to count squares. You get marks for counting squares. Don't try and integrate it, even though that's technically the better method. At A-level, just count the squares if it's curved and estimate using that way. So let's draw some of these motion graphs for some tricky situations. The first situation we're going to encounter is dropping a ball. When it drops, it's going downwards. It's going to have negative velocity, which is a straight line. As soon as it hits the ground at A, the velocity instantaneously, almost instantaneously, changes direction to go upwards to B, and then the same thing happens again. It's going to fall with a decreasing velocity, change direction at the x-axis a few times when it's bouncing. Now, to work out the gradient of the graph, the reason it's straight is because the only thing that's accelerating the ball is gravity, which has a constant acceleration, 9.1. So the gradient at any point of those downward slopes when it's being dropped should be constant, meaning it's a straight line. Now, if I was to draw a distance and a displacement time graph for a similar situation, but this time the ball is projected upwards instead of being dropped, we can notice the difference between distance and displacement. So distance means basically how many meters does the ball cover. So in this case, it goes upwards, and then it sort of stops being a horizontal line, and then it carries on covering distances because it's a scalar. We just draw it kind of carrying going upwards. Now, a displacement time graph will eventually come back down to zero. So it'll reach its peak, and the displacement will then decrease back to zero, meaning the two graphs have a slightly different shape. Let's try and draw an acceleration time graph, which you won't have done at GCSE. Now, for our bouncing ball or our projected ball upwards, the acceleration is always constant, 9.81, as we mentioned earlier, so it's just a horizontal line. Next, we're going to look at SUVAT equations, or equations of motion. Where do they come from and how do we use them? So we're going to derive each of them from this initial equation, which is the definition for acceleration, change of velocity divided by time, or v minus u over time. Now, if we rearrange that to make v the final velocity, the subject, we should find that v equals u, the initial velocity, plus at. Now, if I was to graph this on a velocity time graph, similar to the ones we've just looked at, we will notice for an object that has an initial velocity and is accelerating, its initial velocity u is the y-intercept on that axis. And if I was to work out the area of this graph, the area under a velocity time graph is equal to displacement. So in this example, I've got a rectangle down here, which is area is ut, and this triangle up here, the area of a triangle is half base times height. So it's half v minus u, the difference between them, times by t. Now let's make this look a little bit simpler because it looks a bit messy at the minute. So we're going to group like terms together and separate out the brackets. So ut plus half vt minus half ut. Grouping together ut terms, I've got ut minus half ut, and I've got half vt there. So I'm going to factorise back in, and I've got basically half uv times by t, or u plus v over 2 times by t. So that's our second equation of motion, or a second SUVAT equation. To find our third equation of motion, or third SUVAT equation, we're going to substitute in equation 1 v equals u plus at into the equation we've just found, equation 2. So instead of v, we're going to write u plus at. So we've got u plus at in our brackets, and we're going to group together our u's, so 2u plus at, and then we can start to expand out the brackets a little bit. So we've now got 2ut over 2, the 2's cancel, plus at squared, because we've times the whole thing by t. So rewriting that a little bit differently, I've now got s equals ut plus half at squared, or at squared over 2. Now for the final one, it's a little bit trickier. We're actually going to multiply two equations together. We're going to multiply together, acceleration is v minus u over t, and distance equals u plus v over 2 times by t. So if I multiply those two together, I've got as, or acceleration times distance on the left, and on the right hand side I've got these terms I'm multiplying together here. Now hopefully we can see that one of the t's will cancel straight away, which is quite nice, leaving us with v minus u times by u plus v over 2. So if I times those together, I can kind of combine the brackets together and expand out the brackets. Now if I expand out the brackets, I've then got v squared minus u squared over 2, and to rearrange this to make v squared the subject, we're going to get v squared equals u squared plus 2as, which is our fourth and final equation of motion. Now how do you use each of those? Well, the first one you might notice has no displacement in it. So if you had the velocity, two velocities and acceleration, you could find the time, for example. The second one has no acceleration, the third one has no final velocity, and the fourth one has no time. So you have to pick your equation carefully depending on what information you're given. Now there is a slightly unofficial last equation which isn't on your data sheet for AQA physics, for example, and it says that the distance equals vt minus half at squared. So it's kind of a similar version to equation 3, but just replacing u with v, and that makes the minus half at squared negative. Let's look at projectile motion next. So we're going to apply some of these equations of motions to projectiles. We're going to go back to our original question right at the start of the video, which was if I was to project a ball horizontally and drop an identical ball at the same time from exactly the same position, which would land first. Now well done if you said correctly that they both land at exactly the same time. I'm going to explain why that is the case in a moment. So when we're drawing these, the projectile projected horizontally, we need to consider the components of its velocity. Now its horizontal component, we can see here I'm drawing the same size arrow, whereas the vertical arrow, the vertical component of its velocity, is increasing. Now the reason for that is because we can treat the two components separately. The horizontal velocity is constant, we're not including air resistance here because you've given it an initial velocity which will always be the same. The vertical component of the velocity will be increasing because of gravity accelerating it downwards or towards the earth. Now the velocity, the vertical component is increasing in exactly the same way as the ball that I'm dropping directly downwards. It doesn't have any horizontal velocity, and the arrows get bigger and bigger each time. So actually the factor that determines how quickly it reaches the ground is its vertical velocity, which for both balls is identical. And the big conclusion here is that no matter what its angle it's projected at, you can consider horizontal and vertical components of its velocity totally independent of each other. So what we can use for horizontal motion, because there's no acceleration, we're not including air resistance here, the only equation that applies there is distance equals speed or velocity times time. So the initial velocity is the same throughout. For vertical velocity, however, there is acceleration, so we need to use any one of these SUVAT equations we've just been through, depending on the information you're given and what you're trying to figure out. If you're given a ball that's projected diagonally at a certain angle, what you're going to have to do is resolve the components in the vertical and horizontal direction, the components of its velocity, before you can do anything with it, because we're not considering diagonal components at all. So if you resolve it into the vertical and horizontal components, it's either cos or sine. Draw a little triangle out if you're not sure, so you can get that question right and you don't get the wrong way around. So in this case, it's u, the initial velocity, times by cosine of that angle, and then sine of the angle in the vertical direction.